So let's take an example of this double root situation with this particular recurrence relation along with some initial conditions here. So with this recurrence relation here that I've underlined, the characteristic polynomial would be r squared is equal to 4r minus 4, peeling off the coefficients there on the right hand side. And if we put all on one side, is r squared minus 4r plus 4 equals 0, or r minus 2 squared is equal to 0. So because of that square right there, I know I have a double root of 2, so I'm going to go ahead and scroll up here now. So we have the double root of 2, and I'll often write it this way to indicate that it is a double root, 2 and 2, so double root. So what the theorem tells us, let me go ahead and scroll back up there just a second, is that we get an alpha 2 to the n plus a beta, I'll use a beta instead of an alpha 2, n 2 to the n. So the general solution is a n is equal to some constant times 2 to the n, I'll use an alpha, plus some constant beta times n 2 to the n. So there's that second, or that additional factor here of n when you have the double root. Right, so now with the general solution here, this is the general solution, we can find alpha and beta using the initial conditions. So that's what we're going to do, impose those as initial conditions. So let me scroll up here a little more so I can see how much room we have to work with here. So when a0 is equal to 3, that's n is equal to 0. We would have 3 is equal to a0, right? But that above tells us it's alpha times 2 to the 0 plus beta times 0, that's n, times 2 to the 0, right? N equals 0. So this term here goes away. That goes to 0 because of the 0 there. And the other term there is just alpha, so alpha is 3, right? Because 2 to the 0 is 1. So now let's use a1 is equal to 4 above, and this will be for n is equal to 1. So we'd have 4 is equal to a1, that's given, but a1 by our general expression is equal to 3, that's alpha, times 2 to the 1, plus the unknown beta times 1, 2 to the 1. And we'll solve that for beta, and that is 4 is equal to 6 plus 2 beta, and so that gives us beta is equal to minus 1. So the solution is an is equal to 3 times 2 to the n minus n times 2 to the n. And if we wanted to, we could write that as 3 minus n, factoring out the 2 to the n. Okay? So there it is right there. All right, so I've got some practice problems here, and I'm going to write down the answer for each one of these, and you can use this video however you like now, taking time to pause and try this yourself and then check against the solution. As I say, any particular way you want. But here I go. Here's the first one. So the first one, an is equal to 5 times 4 to the n minus 2 times 7 to the n. And the characteristic roots are 4 and 7 for that one there. Okay. I'm going to have to come back there and check that out. I think that's a minus 4, right? Let's just double check it. I may have been too quick on that one right there. R squared equals 3r plus 28 gives us r squared minus 3r minus 28, which is r minus 7 times r plus 4. So it's going to be a minus 4 there, like so, and I hope I've got it right. Let's check it out. If n is 0, we get 5 minus 2, which is 3. And then when n is 1, we get minus 20 minus 14, Yeah, that's not a very happy situation. That's not going to give us a -1 there. Shucks. Yeah. So I'll come back to that one. Okay. You can get the answer, but I don't have it written down on my paper correctly here. So, yeah. Okay, this one right here, hopefully I have this one right. This one right here would be an is equal to 4 times -3 to the n plus 7. And you might wonder where the 7 comes from. And the 7 comes from the fact that one of the roots is equal to, I'll write the second one, is equal to 1. So this is 7 times 1 to the n, which is just 7, right? So that's odd how that works, but whenever one of the roots is 1, that's the kind of thing that's going to happen there. So this one right here, third one, has a solution. An is equal to -3 times 4 to the n, and plus n times 4 to the n. It has a double root. And again, you could write this if you wanted to as n minus 3 times 4 to the n, like so. This last one also has a double root. In this case, the double root is 1. And so this one right here, the solution turns out to be just a linear polynomial, 6 plus 2n, because each of these has a factor of 1 to the n, which really doesn't do much for you in that particular situation. So let's go back up here and see what we can do with that first one there. I should actually get a solution for that. So the equation for the first one should look like a sub n is equal to alpha times -4 to the n plus beta times 7 to the n. Right, so the two roots being 7 and -4 as I indicated up here. So we have 3 would be the 0 case, n equals 0 case, and that'd be alpha plus beta. And then -1 would be the 1 case, and that would be -4 alpha when n is 1 plus 7 beta, like so. That doesn't look real promising to me. I'm thinking that we might actually run into some fractional problem here, which is not horrible. But again, I'm going to multiply this by 4. That'll be 4 alpha plus 4 beta, kind of like what we did before. And that's equal to 12. So if we add those, we get 11 is equal to 11 beta. Oh, that's not bad. Beta's 1. That's not bad at all. And that means alpha is equal to 2. Just going back up here and putting beta equal to 1 in there, alpha is equal to 2. Well, that's not too bad. So that first one really should be at a 2 and a 1. It should be, let me go back up there and change those to 2 and 1. So that's 2 and a 1 here. In other words, an is equal to 2 minus 4 to the n plus 7 to the n. Okay. All right, well, I gave you another solution there to ponder as well.